Good afternoon, everyone. My name is Paul Prenny, and I'm here today. I'm going to talk about the relevance of OpenCL to HPC. Essentially, today's high-performance programs are evolving to be more parallel, more weight-free, and they're getting deployed on more and more hardware types, including upcoming hardware, and there's legacy hardware as well. The OpenCL standard nicely allows one to deploy stuff to heterogeneous architectures. So whether it's CPU, GPU, some other kind of chip, FPGA, whatever it is, we can deploy to it. And so the purpose of this talk is to communicate what OpenCL is all about at a high level. It's not going to be a programming, and I want to emphasize the relevance of OpenCL to HPC for academia and the research community and those of us that use it, and so we can have a better understanding of this technology. And as always, we want to exploit the future, and to the extent we can do things today, great, and to the extent it happens tomorrow, knowing about it is everything. The presentation overview, the first point, HPC and OpenCL. We're going to talk about that, and then I'm going to go into various points on the relevance of OpenCL to HPC, and give you a glimpse into some possible high-level abstractions involved. Then we'll have a discussion on the future, OpenCL, HPC, all of that with the guest that's here, and you can participate in that. And if you look at the slides after online, there are references for everything in the slides. Okay, so first of all, what is HPC? And I'll answer this more from a Sharcnet perspective. HPC is a lot of things. Certainly it's high-performance computing, but it's the use of parallel computation to solve problems more efficiently and reliably. Important organizations and meta-organizations to know about. Certainly there's Sharcnet, and we're Sharcnet. Compute Ontario, which includes SciNet, HPCVL, and Sharcnet. And of course, under Compute Ontario is part of the umbrella under Compute Canada, which includes AceNet, Calcu Quebec, Compute Ontario, and WestGrid. OpenCL is published by the Kronos Group. So if you go to kronos.org, you can find OpenCL there. They're the same people that publish OpenGL and a variety of other standards. OpenCL itself is open and a royalty-free standard. It can be used with CPUs, GPUs, and any other computational hardware. It provides, very importantly, portable, efficient, heterogeneous hardware access. And it uses a subset of C99. And it's a subset, but they've added parallel extensions which don't exist in C99. Okay? And these the programming abstractions that they've added that are parallel allow you to transparently leverage basically SIMD instructions on hardware and or threading parallelism, so stuff on the back end. Okay? And important to note that through the Kronos Group, all the hardware vendors decide on the abstractions used. Okay? I mentioned OpenGL. OpenCL does interact with OpenGL and other technologies, and nicely they are working on, the Kronos Group is working on a WebCL standard. So basically the same way you would do like a WebGL app and you have JavaScript with OpenCL used through the web with WebCL, you would have your JavaScript submit basically, I guess, OpenCL C code to the back-end part of things so that it can run on devices. So how does OpenCL enable the heterogeneous, different kinds of hardware to be used for computation? Okay, well, there's an API that lets you discover the computational hardware components of the system. So in other words, what devices? So how many CPUs you have, how many GPUs you have, how many specialized devices that can compute something do you have on that system? Basically, there is an interface, and a function calls, if you will. You can call it, and you get this information back. So you can query hardware characteristics. So it's not just, oh, I have so many CPUs and GPUs or whatever on this computer, or a set of computers or whatever the interface is supporting. The hardware characteristics are there too. So if we go for traditional computing, you might want to know about your RAM, your cache, and all this stuff if you're thinking normal CPU. And if you're going to GPU hardware, what do you want to know the specifics? Why? Because it matters for your code. You want to write efficient code. And you would like it if your code could query that, so it can do some if statements, some logic, some artificial intelligence, whatever, to figure out the fastest way or the best way to go about it feels going about to compute the problem, to solve the answer quickly. You do compile your programs, and then you extract the functions that you want to run. Now, when you submit something to an OpenCL device, that beginning of a program, if you're programming in C, that would be like your main. That is called a kernel. If you do GPU programming, you're already used to that term. If you're not used to that term, know that a kernel is just like when you write a C program and you have your main function that gets called first, and the environment gets passed to it, all of this stuff, and then that's responsible for running your job. Okay? On it. There's more gotchas on it if we were to do a full OpenCL talk on the programming, but high level, that's what it is. And the kernel, you'll asynchronously call those kernels. The whole point of OpenCL is for massive ability to parallelize. You, of course, want to be able to control the ordering of some of your operations, and you want to be able to control some aspects of your memory as well for your data. Now, importantly, OpenCL uses something called OpenCL C and other things on, we'll call it the back end. That's the inputs to the device. And what you can do is you can use that as if it were like, even though it's, we'll call it just C, the C programming language, a subset of it, even though it's that, you can think of it like a machine code. And you can have multiple programs and platforms and tools and compilers and all that compile stuff out to this back-end stuff. One of the things that is in there is OpenCL C. And if you do that and then you submit it to the OpenCL device APIs to be run, you can achieve this heterogeneous computing thing. This is a slide from Neil Trevitt's talk at SIGGRAPH Asia in December, and showing how a variety of very distinct technologies can be fed into OpenCL to run stuff on compute hardware. Okay, so you see WebCL here, you got AMP here, you got Haskell stuff, you got some Java stuff, some Python stuff, Intel stuff, etc. So this is very important, and this is a key goal of OpenCL, is to be able to have this kind of thing happen. OpenCL C is, as I said, it's like a machine language, but you wouldn't think of it that because it's a human readable form. It does get compiled by a compiler, an OpenCL C compiler, and depending which version of the standards, the compilers are actually in the device themselves, so the C can be submitted and it will be compiled. In other cases, it might not be, but you can one way or another compile it. And nicely, you use it to create the kernels, the actual code you want to execute in parallel. These kernels are controlled by a host program that runs on the machine that's deploying it. It's based on C99. Okay. There is no recursion. There's no function pointers, so it's not the kind of C you normally want to program in, but it does add vector types and atomic operations and some additional types that are relevant. But pointers are restricted. There's no bit fields. Much of the C standard library is not there, however, the math functions are. And you should know, if you're into C, the memory consistency model is based on the C11 standard in section 717. New for release, this is a provisional specification. This was announced yesterday by Kronos. OpenCL C++, and so there's OpenCL C, which you can write your kernels with. Well, you can also write your kernels with OpenCL C++, and this is based on C++ 14, and it supports templates and metaprogramming. That said, it has the C restrictions because for the same design reasons, and it also has additional features not supported, of which new and delete, no accept, go to register, these kinds of things are not supported because they get in the way of the parallelism. But I must add, it is a provisional specification. So what that means is they're making it publicly available for researchers, for HPC persons like us to comment on, to contribute and move things forward, correct mistakes, whatever. So this is something we should look at and contribute. If you're someone that's eligible for that, definitely do that. If you can contribute other ways, why not? This is meant to be universal and non-proprietary. The kernels group does not worry about one vendor. It is all kinds of vendors together, working together, so this is very non-proprietary. Spear is another important thing. Now, OpenCL C and OpenCL C++ look like those programming languages. Okay? If you look at it, you'll say that just looks like C and C++ code. Spear is different. Spear is, think of it as machine code for OpenCL devices. It's not actually machine code, of course, because the actual hardware that things run on have their own machine code, but Spear gets converted into that machine code. So it is an intermediate language. So if you're into compiler theory, you know it's an intermediate language, and it's partially compiled code. And what happens is this, you can submit this instead of OpenCL C or OpenCL C++ to the back end, to the devices, and that will then take this, we can think of machine code, but it's actually an intermediate representation, and compile it into optimal code for the hardware. And the nice thing is the vendors provide the back-end code for their hardware, which means if you have some chip, and just because Intel is big, I'll just mention Intel, but it could be NVIDIA, it could be whomever, and let's say they have revision 4.3.2.1 of a chip, and that could be more optimal for something, then they can put their if statements in there. You just install the back end, you get the back end and you install it, and your code on the front end goes it. Your code does not need those special if statements. You don't need to worry about it. That is the whole point of OpenCL, OpenCL C, OpenCL C++, Spear here, and of the next slides on related things to Spear. So that is really cool. Now, Spear is an extension to the OpenCL standard, but you'll see in a second there's more to it than that. There's this, also announced yesterday, Spear V. Okay, it's provisional, so like the OpenCL C++, this is open for input. This is an intermediate language. And Spear itself, the previous slide, is based on the LLVM intermediate representation. Some of you may better know LLVM as the C-lang compiler. Spear V does not depend on the LLVM IR in any way. It's its own intermediate language. It supports graphical shaders, so your graphical operations, of course, and general compute operations. I took a quote here from the provisional specification that was published yesterday, that Spear V is a single common language from multiple languages feeding multiple drivers, where the drivers here are the hardware that you're running your compute jobs on. This also comes from an announcement made yesterday for something called Vulcan. And what it shows here is that you can have game engines, okay? You can have shader sources, you can have future tools and all that. All compile those programs to Spear V, which is, you think of it like an exe file. If you're not into compilers, you're not sure what they all are, what they're all about, think of it as an exe file for OpenCL. And, but it's not, it's an intermediate representation, but you can think of it as such. And it gets combined with things, OpenCL infrastructure and this Vulcan stuff that is a separate thing, and it gets deployed on multiple devices. I should mention the whole thing with Vulcan, if you read the press release on Kronos.org, the whole thing with Vulcan is merging compute with graphical computations. So basically your graphical stuff with GPUs and what you do with graphics and general purpose but high performance computing use, putting all that together, OpenCL stuff. Vulcan, to the extent I understand it, represents the merging of those. Obviously it's just posted yesterday, so not much time to figure that out, but Kronos.org has those press releases. So let's take a look at the relevance of OpenCL to HPC. Essentially, before going there, I want to just emphasize that OpenCL defines a whole bunch of things in it. You have a bunch of hardware vendors also involved with this. And all the hardware vendors are working together to agree on this thing called OpenCL. And what do they agree on? They agree on things like OpenCL C and OpenCL C++, the Spear, and the Spear 5. So from our point of view in Sharcnet and other HPC facilities, you write your programs, you compile your code, you do these things. That's wonderful. Instead of compiling it to a machine code for one chip, whether it's AMD, Intel, NVIDIA, or whatever, and it only works on that one revision of that one chip with that compiler, if you used OpenCL technology, you would be able to build your code, compile it out to whether it's OpenCL C, OpenCL C++, the Spear or the Spear 5 stuff. Don't worry about it. Those are the back-end inputs. You compile it out to those back-end inputs with your tools, and you can run your code. Now, I'm talking a little bit there in the future because today we still write a lot of low-level back-end stuff, but increasingly there are more and more tools becoming available, so we don't have to write all those nitty-gritty low-end back-end stuff. It's no different than if we rewound the clock back in time. People used to write machine code, then we went to assembler, and then we kept graduating to higher and higher levels. This is an evolution as well. So why does OpenCL matter to researchers, academia, high-performance computing persons? Okay, OpenCL can be run across many different devices. You do not have to redesign, refactor, or rewrite your code. Okay, that's wonderful. This is one of the things that's why OpenCL C, C++, Spear, and Spear 5 are so important, that those technologies that are part of OpenCL allow that to happen. Okay. Nicely, the host code that basically deploys the back-end code also is non-proprietary. It's a nice API. If you read the OpenCL standards, you'll see that it is a bunch of function calls and you get information. It is not tied to any one vendor. It is to support whatever vendor supports OpenCL, and you get the backends for that, and you install them, and then you're good to go. Okay, and very nicely, you have the ability to query and exploit device-specific abilities, and this includes, let's say you, for some reason, really needed to use a feature that's only on some chips that's very specialized. Okay, you can query that from the device to make sure it has it, and if it does, you use it. And if you're part of your program's running on another device that doesn't have it, you can compensate for that. You can say, oh, it's not there, we'll do it this other way instead. So you can make your code tailored to devices that are running and be independent of the underlying actual chipsets being used. Why does OpenCL matter to high-performance computing? Well, bottom line, heterogeneous computing is the future. Those of you who have done stuff on Sharcnet, Sharcnet's hardware is not all homogeneous. You've got tons of different hardware all over the place. They're similar, but there's differences as well, and plenty of them. OpenCL is geared to exploit all of the different kinds of hardware well and efficiently as a standard. And you don't have to sit there and say, oh, I just optimized all my code for this chip. What do I do now when I'm going to move it to another cluster and it's a different chip? Well, if it's OpenCL, your life's easier, much easier. But if it's hard-coded to the chip, then you got a lot of work to do. So another reason, power is very, very costly. These servers and clusters and all of these other things that are running consume power, lots of it. Okay, it costs money, and really cool today if you're following things and green computing and all that. Specialized circuits that can do very high performance stuff like number crunching. What we're seeing is we can get lots of performance for limited number crunching and drop the power requirements. So you're seeing more and more specialized chips being able to do this, and the power amounts are very significant. So there's FPGAs and different things like this. OpenCL deploys to all of these hardware components. So very nicely, you can exploit it if you're programming in OpenCL, even though you've never used that chip before. If you have your OpenCL code, you can deploy your OpenCL software to that chip and allow that to be leveraged. You want to maximize your parallel performance. I didn't say, but OpenCL C, C++, and essentially the design of Spear and Spear V all allow for massive vectorization and parallelization. The only construct you can do any sort of synchronization on within the kernel is the atomic operation. And nicely it works with floats too, so those of you doing needing atomics, you can use it with floating vectors and all that in OpenCL C and C++. But that is a shift in your programming. You cannot use locks, semaphores, mutexes, and all that. They don't exist in OpenCL C and C++, and this machine code equivalents, the Spear and the Spear 5, do not do that. The reason being is the hardware vendors want to be able to deliver maximum performance. So if you give them their inputs, they will give you maximum performance with that. And if you put locks in there and all these other things, that will just kill the performance. OpenCL enables stuff to be deployed on future hardware designs, okay? And it has very major traction and support with hardware vendors. So that's extremely important. It's not just one vendor. You have all the major vendors across the board that I can think of that are significant involved, which is wonderful. Quick couple points on OpenCL. You should see each standard as a distinct release. There's this tendency, I'm guilty, we're all guilty, and you see a new release number, you know, and you think, oh, this is new and better. I've been told that you should see it as a distinct release. Vendors will release OpenCL implementations for different versions. There may be technical reasons for that, but that's okay. And they're not better or worse. They're just different. So don't write off OpenCL 1.0 just because you see there's 2.0 or the provisional 2.1 that was published yesterday, whatever. Each standard is a distinct release, and they're different. And some hardware vendors will choose to do 1.0, 1.1, or 1.2, whatever. They'll choose those for reasons. Some will support all. They will document that in their releases. That said, when you program with OpenCL, you want to think of OpenCL C as a very high-level, heterogeneous, portable, human-readable, parallel assembly language. Of course, it looks like C code, so that's nice. It looks like C code. You do not have to think like an assembler coder. But that said, you do have to understand the memory models for parallel programming and the how to write parallel code if you're going to write OpenCL C directly. You should think of Spear and Spear 5, or not Spear V, sorry, as a machine code, if you will, for OpenCL. It is an intermediate representation, so if you are a computer science or computer engineer, computer scientist or computer engineer, then it is an intermediate representation. You know that intermediate representation on the device or somewhere gets compiled to the actual code the chips run. So beyond the short-term future, okay, realistically, you as an OpenCL user do not want to write raw OpenCL code when developing your program. Ideally, you know, if us computer scientists and the computer engineers of the world do our jobs, we provide you wonderful abstractions, high-level programming libraries and middleware and tools that you could write your codes in instead, and that gets converted into this stuff for you. There's a variety of reasons for that, but there are differences, for example, between the OpenCL standards, and if we do our job writing abstractions, libraries, and middleware, then that won't be your worry, because part of what those abstractions are and the middleware is it will take care of figuring out which versions of which standards features are or are not, and properly deploying and executing things. Before we go to the discussion, I wanted to give you a glimpse through some examples. My guest here has provided of OpenCL C, and because everyone likes to see some source code, so I'll show you what some of the source code looks like, what some of the C++ code could well look like for the host code and the new provisional OpenCL C++. Here we have the beginning, here we have the complete OpenCL C kernel. So this code that you see on this slide will be submitted to an OpenCL device, and that OpenCL device will compile and run this code. As you can see, we have the __ kernel that just says the sum function here is a kernel, and we have __ global that just says it's in the global memory pool. And the global memory pool, keep it very simple, everything has access to it. And that makes sense because if this is your main of your program, you need to pass it data. And that's the purpose of those variables. We have out, in1, in2, and we have a length variable. We have the notion of various IDs in OpenCL. This one gets the global ID, and the if statement checks to make sure that it has a valid value before running any code. If it doesn't, it just returns. And then nicely at the bottom there, that one-liner, if you were programming in actual C code, in normal traditional C, that would be, in a sequential program, that would be a for loop, okay, if float was an index, okay? This is code you have, and it's a for loop, and it will go through all the indices. I'm wondering if the type's missing there, but if we had, float star there, these can be, these would be typically arrays at this point, and then you can have vector operations. So if you want to add up all the pointer values at once, you have your index, you have your global ID, there's a length passed in, and what this will take care of is adding up all the in values to the out value, to the in1 with in2, and put each corresponding value in the out. So this is no different than vector addition. In1 and in2 would be your vectors, and out would be where the vector is received.
I want to point out one thing to you, Paul, and that is just that if you note you don't know the number of lightweight processes or software threads for this example, and you don't know the vectorization, because the implementation will automatically use it.
Okay, that's a very good point. Notice in this code, there's nothing about how many instances of this code is running. There could be one, there could be hundreds, there could be thousands, whatever. Okay, that is not in this piece of code. That allows it to be parallelized very nicely because you don't have all that junk sitting in here. The global IDs are special. I should say the IDs in general are special, and that talking about how the stuff actually gets run would be probably a couple talks unto themselves. So And nicely, the Kronos group has made sure they don't pollute OpenCL C with junk that doesn't need to be there because it would interfere with making things massively parallel. So, so that's why there's missing features. So if you love C and your favorite feature is not there, don't complain. Find out why it's not there by seeing what you can do with it. And you'll appreciate that they didn't put it in there because that would have impacted performance. Now, in order to deploy that code, the sum code, okay, you need to write your program. So if we have this C++ program, this would run on, let's say you just your host program is running on a normal Intel or AMD CPU, which is running on a normal CPU. On your computer, you have some graphics processors and some other hardware that OpenCL can take advantage of. That's fine. So you compile and run this program. This is a subset of a program, of course. We have this is high level, this is conceptual, there's some abstractions here, it's not actual OpenCL code. We want to get the list of devices. We would compile the previous slide's sum code in the next line, okay? And then once you compile it, you get a kernel object back. You can just think of this as a special object that the library, the APIs return, okay? Now, if I go back one slide here, you'll see that we have our floats here. And it does say stars, so these are pointers, in fact. And so we need to be passed in our inputs. So we actually have to take care of, before we deploy our jobs, we have to allocate all the memory. Recall I said OpenCL C++ does not have new and delete. Well, guess what? You don't have it in C either, the no mallocs and all that, right? So you're going to have to allocate your memory before the job gets deployed. So you basically set that up. So we have allocate vector here with size of 100 for X, Y, and Z. Okay. Notice it's X, Y, and Z. There's an output vector as well. Okay. So we have X equals, we'll read in our values, and Y equals, we'll read in our values. And then what we'll do is we will use the kernel object we got back, which the variable was called sum, and we'll call for all devices, okay, I should say the devices corresponding to offset 0 there, okay, we'll call our function. And notice we have 4 arguments there. Those 4 arguments correspond to the 4 arguments passed to the sum function. So I'll just jump back here. We have out, in1, in2, and the length. So there's the 4 arguments, and we do the same thing with y. Okay? And when we're done, we want to print the results. Now, this omits a lot of the lower level OpenCL API calls. So these calls here are abstracted. Inside, there would be OpenCL calls to do the actual jobs. Now, just to show you, it's new as of yesterday with the provisional release, OpenCL C++. I could show you C++ code with it, but this is a nicer example because it shows some template metaprogramming. Most people don't do that, but if you do template metaprogramming, here's an example. And in particular, it's using numeric limits to actually make decisions on the type representation based on aspects of the double type. So is double supported and it's not emulated? And you might say, wait a minute, why would you even care if double supported? Well, some news, OpenCL C and OpenCL C++ support of double is optional. Hardware may do it or may not, and that's one reason why you need to query the device to find out the features. And it's possible that the double is supported in an emulated capacity, in which case you'd want to use the double that was emulated, is because it's provided by the hardware vendor. And that's why that conditional code is there. So that can simplify some of the code that would be deployed to devices if you're into C++ metaprogramming.
I want to put out one last thing about that. So, I mean, the key thing with this example and why I provided it to Paul is to show one potential future. I mean, as OpenCL C++ is provisional, nothing set in stone at this point. But this is a nice little fragment that I wanted to show because what's happening is we're actually changing how we're going to compute something. This is going to be inside of a library based on what we found in the hardware. So you can do something very powerful here, which is that you can make a decision in terms of the strategy you're going to use to compute some high-level concept based on what you detected the hardware has. And I think that, I mean, this is templated code, this is C++ code. At the highest level, you're just going to call a function. But library developers like myself or like Paul can then go ahead and make something that is very optimal for you to just pick up and use. So that's what I want to point out.
Thank you.